Here we go. Section 3.1, the derivative. The derivative of a function with respect to the variable x is the function f prime. I don't think you can see that here. It's the function f prime. There's a little prime on there. Okay. Whose value at x, provided the limit exists, is given as such. This is the definition of the derivative. F prime of x, the derivative of f, with respect to x. It is important which variable we are taking respect to. That's the derivative of the function x with respect to function f with respect to x. Is the limit as h approaches 0 of f of x plus h minus f of x over h. You will get an equation out of this. The derivative is an equation. Okay, the derivative describes what's going on with the function. We've talked about this. We've had this rule before. This is what we ended the last chapter on. This is the same definition of the rate of change, the instantaneous rate of change. The derivative gives us an equation that describes the rate of change of the original function f. F prime is a description of the rate of change. An equation that gives us how fast something is changing. An example: if I have an equation that describes where something is, its derivative would be its velocity, how fast that position is changing. If I have an equation that describes the velocity of an object, the derivative of that would be its acceleration. The acceleration is change of velocity over change in time. That is what it was originally designed for. It is expanded to much more. Anything that changes, we can use the derivative to figure out how it changes, describe how it changes, and evaluate those changes. So you can kind of get an idea of how important calculus became. Like I said, it describes how things change. Now let's just evaluate those changes. And everything changes. Almost nothing is static. So this is an extremely useful form of mathematics. That's where it came from. Now, scroll up a little bit. If f prime exists, we say that f is differentiable. Yes, that is the word, differentiable, at x. A function that is a derivative at every point in its domain is a differentiable function. Not every function is differentiable. There are a few exceptions. We will not discuss those today. We will be discussing those on a future date. Almost every function is differentiable. There are a few that are not, but usually when they're not, it's at a particular place. And we'll talk about how to figure out where those happen. Yes? That means you can take its derivative. Like I said, pretty much everything is. There are a few exceptions, most of which we won't have in here, but there are some exceptions we will talk about. Okay, symbols of differentiation. This is really important. There's a lot of notation for how to take the derivative and taking the derivative. This is strictly an introduction. This is not an exhaustive list of the notation for a derivative. One of the most confusing things that students have, particularly early on, is what do they want me to do? They want to take the derivative. That means take the derivative. What do they want me to do? That means take the derivative. That's a notation for take the derivative. Find dy dx. Okay? So we have dy dx. That's the most common. If you have a function y in terms of x, y equals 4x squared plus 2x minus 3. Dy dx is the derivative of y with respect to x. And this is what we say. We say dy dx, or we say the derivative of y with respect to x. That is how we pronounce dy dx. That's what it means. F prime of x. We've already talked a little bit about f prime. Okay. There is y prime. If it's y equals instead of f of x, we can use y prime. Same thing, derivative. Y prime, dy dx, f prime, same thing. Just different forms of saying the same thing. Okay, d dx of f of x. okay, or the derivative of f of x. D dx means taking the derivative of x. When we get the d from delta or change, dy dx is the change in y over the change in x, technically. But dy dx, that is just a notation. Like I said, dy dx, f prime, y prime, d dx of f of x. It could be g prime, it could be h prime, it could be v prime. Any function notation is that prime of whatever variable. V prime of t would be the derivative of the velocity based on time t. Okay, and then we have the all-important one, Optimus prime. Okay, example number 1, find f prime using the definition of the derivative, and I promise this will be the last time you have to do this, okay, because we're going to start learning shortcuts coming up. But you do have to do this. Find f prime of x using the definition of the derivative if f of x is equal to 2x cubed. Write the equation of the tangent line to this curve at x equals 2. So first thing we need to do is we need to find f prime of x. And we do that by using the definition, the limit as h approaches 0, of f of x plus h, which is 2 times x plus h cubed minus 2 times x cubed all over h, as h approaches 0. F of x plus h minus f of x. So f prime of x is equal to the limit as h approaches 0. Binomial expansion, x cubed plus 3xh times 2. If I multiply 2 times them as I do this, so it's 2x cubed, right? 1, 3, 3, 1 times 2, 2 times 3, so that's plus 6x squared h plus 6x h squared plus 3h cubed minus 2x cubed all over h. So if I do the binomial expansion of x plus h cubed and then multiply those terms all times 2, that's what you get. Trust me on this one. Okay. And this is actually the only time I ever use the binomial expansion theorem. Don't tell my algebra 2 kids that. Okay. No, I never use it. This and that cancel, the 2x cubes cancel, and then I can reduce my h's, this h and that h, and one of those and one of those. And now I can go ahead and take my limit, right? Because I no longer have h in my denominator. So I can go ahead and let h go to 0. So f prime of x is equal to, let h go to 0, and this one disappears and that one disappears, and I get 6x squared. That's my derivative. Okay, yes, question. Okay, so that's the f prime. Okay, this is the equation for my derivative. Now, part 2 of this. Write the equation of the tangent line to the curve at x equals 2. So you need 3 things for a tangent line, right? X coordinate, y coordinate, and slope. We have the x coordinate. The x coordinate was given to us. Somebody was really nice, i.e. me, and gave us the x coordinate. How do you find the y coordinate? In the original problem, plug in 2 in the original problem. My y coordinate is f of 2. So that's 2x cubed, 2 times 2 cubed, which is 16, right? Okay. How do I find the slope? The derivative. Remember, the derivative is the equation. This equation describes the rate of change of this equation. How fast is that changing? It's changing 6x squared at any point x. This equation describes how that one is changing. So if I want to find the slope, my slope is f prime of 2. Because remember, how did we find the slope? We used the definition of the derivative to find the slope earlier, right? This is a general equation for the slope rather than a specific point. So I do f prime of 2, which is 6, times 2 squared, which is 24. And then we do my favorite equation. Well, it's probably the one I use more than any other, literally any other equation, any other formula, at any time. This is the most used one if I add all my classes all together. Because anytime I teach anybody how to write the equation of a line, this is my go-to fallback for any equation of a line. It works every time. Plug in my y-coordinate, plug in my slope, plug in my x-coordinate. And then if I need to rearrange it, I rearrange it. But literally, I just got done working with my Algebra 2 kids on that. And of course, they blew the equation with it. That's okay. No, I don't have to do lines. I don't have to study this crap. Yeah, well, yeah, they did. Okay, but yeah, this is probably the most used formula in all my classes combined. Okay. And it says write the tangent line. This is an equation of a line. It has x and y and a bunch of numbers and an equal sign. It's a line. It's a line. It may not be y equals. May not be ax squared plus bx equals c, but it's still the equation of a line. And as far as I'm concerned, stop. Do not rearrange and mess it up. We'll see how many of you listen to me on the test when I read that last page. Okay. Alternate form of the derivative. This only works when you're looking at it, when you're looking for it at a particular value, or you're trying to find it for f of a. It's one that doesn't work well though. Okay? Bless you. Bless you again. So this one really only works if you're looking for the derivative at a particular point A. Okay? That's what this is. That's what this one's designed for. This is not designed for a general derivative. That's what the previous one's all about. This one is, do I want the derivative at a particular point A? Okay. So, I want to find the derivative because I want the equation on the normal line, so this curve at x equals 4. How do I find the equation on the normal line? I need the equation of the tangent line. I'm sorry, I need the slope of the tangent line, and it's the reciprocal opposite of that. It's because they're perpendicular. So I need to find f prime of 4. So this is the limit as x approaches 4 of f of x is the square root of x. So it's the square root of 4 minus, the square root of x minus the square root of 4 all over x minus 4. Because a is 4. Can I plug in 4? No. So I got to do some algebra. Now, I know that many of you are strongly tempted to say, well, isn't that x square root of x minus 2? Trust me. Trust me. I have, within my denominator, the difference of 2 squared. Do you see that I have the difference of 2 squares in my denominator? This does not look like your standard difference of 2 squares. However, if yeah, anything minus anything is the difference of 2 squares. This is the square root of the first plus minus the square root of the second. Anything minus anything is the difference of 2 squares. It does not have to be your typical x squared minus 9. That's what everybody thinks of, the difference of 2 squared. Why if something minus something, it's the square root of the first object plus and minus the square root of the second object. Difference of 2 squares. And looky what I can do. Okay. So that's the limit as x approaches 4 of 1 over the square root of x minus, or sorry, plus the square root of 4, which is, can I plug in 4 now? Yeah. Square root of 4 plus square root of 4 is 4. Normally it doesn't work out that way, but it does with this particular one. So it's 1/4. So the slope of my tangent line is -4. No, sorry, the slope of my tangent line is 1/4. The slope of my normal line, is -4. My x is 4. My y coordinate, what's my y coordinate? My original equation was what? Square root of x. Why not -2? No, square root of 4, because if I take -2 and square it, don't I get 4?
That's right.
So isn't the square root of 4 either 4 or -4? Okay, there's a problem with that. If you consider both negative and positive radicals, then when you take the square root of 4 and you consider both possible answers being 2 and -2, you no longer have a function because one x has 2 y's. One x is not allowed to have 2 y's and have it still be a function. We do not take derivatives of non-functions. We kind of do sometimes, but that's a whole different other story. Wait, no. There are exceptions, and you'll see the exceptions. But for the most part, we don't. So y equals the square root of x is not a function unless we limit the range. And we must say y is supposed to all be positive, so we're only dealing with the stuff above the x-axis. We have to, otherwise this never works. Y minus 2 is equal to -4 times x minus 4. When all is said and done. Okay, we have to be careful, and in your textbook on some of your homework problems, it gives domain limitations. It gives range limitations. Why? In order to make it so you can technically do the work. Okay? Okay. A function f of x is differentiable on the interval from a to b if it has a derivative at every interior point of the interval, and the limit as h approaches 0 from the left, and the limit as h approaches 0 from the right, exists at the endpoints So in order for you to be able to have the derivative, the right and left-hand limits need to be the same from both sides. For a limit to exist, right, the limit from the left and the limit from the right have to be the same. That applies to the definition of derivatives as well. The derivative exists if the limit at that point exists. And the only way the limit at that particular point exists if the limit from the left and the limit from the right following the definition of the derivative. If the derivative coming from the left and the derivative coming from the right are the same, then the derivative at that point exists. This is where the definition of a derivative comes in importancy. Because this is one of the times, if I come at it from one point, if I come at it from the left and I come at it from the right, and I don't get the same thing for a particular value, the derivative does not exist at that point. Now, usually, 90% of the time when the derivative doesn't exist, it's at a particular value that it doesn't exist. Something is off that particular value. We'll discuss that in more detail coming up, but we are going to do an example of that here today. Okay. So example number 3, show that the following functions has left and right hand derivatives at x equals 0, but no derivative at that point. So, in other words, using the definition of the derivative, it's given to you there. Find the derivative of x squared as x approaches 0 at 0, and 2x at x equals 0. To show that they are not the same value. So you need to do it on the left-hand side and the right-hand side. On the left-hand side, what function am I using? X squared. On the right-hand side of 0, what am I using? 2x. So you need to do what I just did for x squared and for 2x and x equals 0. So you need to find f prime of 0 for the limit as x approaches 0 for it's f of x squared minus 0 squared over x minus 0. F of x minus f of a over x minus a. And then you also need to do f prime of 0 on the other side of 0. X as x approaches 0. 2x minus 2 times 0 over x minus 0. And prove that those two are not the same. Okay, that should not have taken very long. If you look at this one, this is really nice. That simplifies down. This reduces. So I get the limit as x approaches 0 of x, which is 0. So my left-hand limit is 0. And this one, these cancel here. That cancels. So I have the limit as x approaches 0 of 2, which is 2. So my left-hand limit and my right-hand limit are not the same. Therefore, the limit at 0 does not exist. Therefore, the derivative at 0 does not exist of that function. Here's why. Graphically, look what's going on here. My right-hand one, I got this nice little curve. My left-hand one, I've got this nice little half parabola. The other side, I've got a straight line. What is happening at 0? If I zoom in close enough on a curve, what do I get? I get a straight line, which means I can find the slope of a curve, i.e. the derivative, the equation that describes that straight line on any curve, right? But what about a point? If I zoom in on a point, no matter how close I zoom in, what's it going to be? It's going to be a point. There's never going to be a line that's going to be tangent at a point. There's not a slope of a point. Where two things come to a point, there's no slope there. There's a slope leading up, the slope leading up. But at that very exact spot, there's no slope. There's a slope along here, there's a slope along here, but not right there at that exact point. That's what's going on. That's what's happening there. That's why the derivative doesn't exist. Because the slope on one side and the slope on the other side of that point are not the same. Which means if I zoom in on there, they won't ever line up. The slopes won't ever line up. And they have to line up or you don't have a derivative. Okay. Graphing f prime from f. I have a graph of my function. I do not know the equation of my function. I don't need to find the equation of f in order to find the graph of f prime. Not nearly as hard as it sounds. However, this is something we're going to be working with an awful lot. Remember, the title of your book is Calculus, Graphical, Numerical, Algebraic. Graphical is an important part of it. You have to be able to interpret graphs. This is f. I wish to graph f prime. I want to graph f prime. This is f. I want to graph f prime. Here's what you do. Find the important points first. Remember, the slope of this is the value of my derivative. The definition of the derivative is the same as the definition for a slope. So whatever the slope of this is at a particular value of x is what the value of that is at a particular value of x. The most important places are where I have my zeros. What do we always look for? We always look for our zeros. So where would I have a tangent line that has a slope of 0? What kind of tangent line has a slope of 0? A horizontal one. So right here, I have a horizontal tangent line. I'd call that about, for ease of graphing purposes, I'd say at 4, I have a slope of 0. The value of my derivative is the value of that slope. The value of my derivative is the value of that slope. That's why when x equals 4, my derivative is 0, because on the original equation when x equals 4, it has a slope of 0. Okay? I'd say right around here, that's about a slope of 1, wouldn't you say? So I'd say right about 1.5. I have a slope of 1, so that means the derivative at 1 is about 1.5. Right about here, my tangent line has a slope of -1. I'd say that's about 6. It's close enough for what we're doing here. My slope is -1. Looks like that. And what happens as I go along? This becomes steeper and steeper. At like 7.5, that's a really steep slope. That's probably closer to about, what, -4, -5, somewhere around there. -6 would be fine. So at 7, I can go down to about here. If I go here at about 1.5, I got the same thing going on. That's about 4. So 1.5, I'm about 4. And just kind of connect up the dots as best I can. Really, that's what you can do. Okay. This is more fun. graphing f from f prime. Now, down at the bottom, you'll notice two very important items that we need to know. One, f is continuous. That means there are no breaks in my original function. Everything's connected to everything else. Two, it passes through a particular point. If I don't have at least one particular point that it passes through, I cannot give a specific original function. I can just give a general one, what it might look like. But I do know that it passes through the origin. My original function f goes through the origin. And here's what's really cool. So from 1 to negative infinity, my derivative has what value? Nah, this is f prime. My derivative has what value? Negative 1. This has a value f prime. F prime equals negative 1. So from 1 to negative 1, what's going on with my original function? It's going down at a slope of negative 1, right? That's what's going on here. So that's that portion of the line. From 1 to 2, what is f prime? 2, which means my original function has a slope of 2. Now, but where do I draw it from? It's continuous. It has to go from here. Slope of 2. And then from 2 to infinity, f prime has a slope of 0. What kind of a line has a slope of 0? Horizontal line.
Yeah.
Okay.
Woo. Yeah.
You will get much better at doing this as time goes on. We will do an awful lot of interpreting, finding f and f prime, going back and forth between graphs of the derivatives and graphs of the original function, and interpreting their values. This is just a baseline. Do not panic. You're going, I don't get it. Okay? Shh. Okay. This one's a nice one because my derivatives are all what? Straight horizontal lines. Which means that my original function are all straight lines. If the derivative is a constant, your original function is a straight line. Because what's the slope of a straight line? It's a constant value. So when you get curves, that things get funky. Okay? That's it.